Yeah, I've forgotten about that little fun fact. I spent already half my life on but it's a fact. Okay, so my name is Anthony Brown, and we'll be talking about uncovering the oldest stars in the Milky Way. So we're going to go and look for the oldest bits of the fossil record of the formation history of the Milky Way. And then in the following talk, we will learn more about the very first stars. So first of all, this is a beautiful image of the entire sky that was made based on Gaia data. So this is not actually a photograph of the Milky Way. This is composed of 2 billion points, of which we know the brightness and the color, and then we can put together such a map. So you can recognize across the middle the band of the Milky Way. You can very nicely see outlined clouds of dust and gas in between us and stars. And basically what we want to do is we want to find out, first of all, what does this actually look like if we were able to go outside our galaxy and take a 3D picture. This is why we measure distances with the Gaia spacecraft. That's this spacecraft over here. And we've been doing that since 2014. The mission has stopped operations at the beginning of this year, and Gaia is now in fact in a retirement orbit around the Sun, but we've collected over 10.5 years of data with which we can study the structure and the history of our own Milky Way galaxy. Now, one of the things that Gaia left behind is a well-informed new map of the Milky Way galaxy. This is a poster that was produced by the graphical skills of Stefan Benoit in Heidelberg in cooperation with ESA. And it's not directly representing the Gaia data, but it's informed by what we found with Gaia. So as it says, you are here. We're at the position of the Sun. We have beautiful spiral arms in the disk of the Milky Way, so you're looking on top of a flat disk. Here in the middle is where we have the center of the galaxy with the well-known supermassive black hole over there. And if you look closely, it's a bit hard with the light. You can see a small galaxy over here. This is called the Sagittarius dwarf galaxy, and we'll come back to that later in the talk. Now this is the top view of the Milky Way. Again, a very beautiful new image that we were able to make based on the information from the Gaia spacecraft. And if we look from the side, it looks like this. So we have a flat disk in which we are orbiting ourselves around the center of the Milky Way. And we know from various observations, including lots of new information from Gaia, that the outer parts of this disk are slightly bent. This is so-called warp in the disk of the Milky Way. And this can now be really well measured with Gaia and characterized also in terms of how the stars move, etc. But that will not be the main topic of today. So today we really want to try and learn how can we figure out the formation history of the Milky Way. And to do that, we do exactly what we do in archaeology. We want to try and dig up the old fossils to interpret them and see if we can find out how the Milky Way came into being. Okay, so I think now we have a short simulation movie that shows how we think galaxies form. So we're starting not too long after the Big Bang, a couple of 100 million years after the Big Bang. And the first gas clouds are starting to fall together under the influence of their own gravity. And in the middle, and that's zoomed in over here, you will see stars forming from the gas, and hence the galaxy coming together. So this is about 13 billion years ago, and we see the very first fragments of this simulated galaxy forming. This is not our Milky Way, this is just a simulation, but it gives a picture of how we think the Milky Way might have come together in the past. And what we want to try and do is reconstruct this particular the formation history of the Milky Way itself, to try to replay what you see here in this simulation. So we're now approaching about 10 billion years ago, and not too long from now some more dramatic event will happen in the life history of this forming galaxy. And it's not unlike what we think happened in the past to our own Milky Way. So right now, if you look over here, there's a large fragment, another galaxy falling in, and it's going to crash into the disk of the Milky Way, as you see over here, of the forming galaxy. And you can see it realigns, and there's a couple of more passages of this thing as it's eaten up in the galaxy that is forming and growing larger and larger. And you can see now also there's nice spiral arms, and it sort of looks like the picture that we had in the beginning of our own Milky Way galaxy. So once again, this is simulation. This is not what actually happened. This is just in the computer. But we want to try and reconstruct the same thing for our own galaxy. And the question then is, how do we do that? Now you can see that this is a very dynamical process. So it seems clear that one of the things that you will have to do is you have to know about the motions of the stars. But the other thing, of course, is we need to put a time order on things. That means we need to know the ages of the stars. It's like when you dig up archaeological artifacts, you want to date them. You want to know how long ago these things were put in the ground in order to reconstruct something about the history, let's say, of Leiden. So how do we do that? So Gaia measures fundamental properties of stars. First of all, the distances to the stars, so that you can actually reconstruct these three-dimensional pictures of where the stars are. But Gaia also measures the motions of the stars. I'll show an example just now. I forgot to switch to this slide. So this is basically our archaeological dig. We are sitting here somewhere in the middle of the Milky Way, the Milky Way disk. We're looking out and we're seeing stars in the sky. And we know more or less what it looks like, but hidden in all these billions of stars are the oldest fragments of the Milky Way, the first ones that came together many billions of years ago. And we want to try and find them. And what I want to try and sketch is, it'll give you a little bit of an impression of how we do that. So first of all, we need to know the motions of the stars, and this is a simulated motion based now on actually Gaia data of how the stars move across the sky. And this is the prediction of the positions of stars about 1.5 million years into the future. But this is just to give you an impression of what Gaia does. It measures repeatedly the positions of stars in the sky, and then we know how they move across the sky. And because we know how far away the star is, we can figure out its motion in 3 dimensions. So we can fully characterize the motions of the stars as they orbit the Milky Way galaxy. So this is two very fundamental properties, distance and motion of the stars. Now there's more that Gaia measures. We have two special instruments on board. These are two prisms that are in the light path of Gaia, and they split the light into its colors, and that's how we can characterize all the stars in terms of their astrophysical properties. Think about the temperature of the star, think about the age of the star, but also we can say something about the chemical composition, so the kinds of elements that you can find in the star itself. And we have a third instrument, that's this optical block over here, which can measure high-resolution spectra. So both instruments split the light into its constituent colors, but this one does it at very low resolution, so you get a very rough idea of what the color content is of the stellar spectrum, and this one does it at high resolution, so that you can in very great detail measure the composition of, for example, what's inside the star. And this is illustrated here. So this is one of the so-called spectra from these prism spectra, so these very low resolution elements. You have here the color coding for the wavelength from the blue to the red, and the particular shape of this energy distribution tells us a lot about the star. It tells us primarily, in this case, what is the temperature of the star, but if you look at the details, you can say something in combination with knowledge about the distance, you can say something about the age of the star, and you can also say something about the chemical composition, which is illustrated a bit better in this diagram. This is data coming from this high resolution spectrograph, so now you see a very tiny portion of the spectrum, only about 50 nanometers or so in wavelength. And what you see is the various spectra of different types of stars. And what you will notice, if you look at the list over here, these are all the elements of which we can determine whether they exist in a star or not. And you see for some stars there's many of those, and for some stars there's almost none of them. And we're particularly interested in the stars where you see almost none of those elements that are heavier than hydrogen or helium, the so-called metals. They're very simple in astronomy. We call everything heavier than helium. We say it's a metal. And we're interested in the very metal-poor stars because they tend to be very old. So if you can find those, then we can hope to say something about where are the oldest fragments in the Milky Way hiding out. Okay, so what we're going to do now is we're going to combine all this information. We have information on the distances, we know the motions of the stars in space. Thanks to these spectra, we can also measure the line of sight motion of the stars, so we characterize it fully. And we can say something about the ages and the compositions of the stars. And remember, we're looking for stars where we have very little elements except for hydrogen and helium, which means that the atmosphere has very little of these spectral lines. And we can identify them with both these types of data. Now here's the first example of going back increasingly in time. So what we have here is again this very nice image of the disk of our Milky Way seen side on. And this will illustrate the motion of a typical star as it goes around the Milky Way in its orbit. It will tend to go around the center of the Milky Way in a circular, more or less, orbit, but it also moves up and down through the disk continuously. And what we can do is we can plot this up and down motion, so we can show that in a diagram by plotting on one axis how fast the star is moving up and down, and in the other axis we can plot how far or above or below the disk of the Milky Way the star is. And normally we expect to see nothing interesting in such a diagram, but what we actually see is this. So this on the vertical axis is the motion of the star up and down, how fast is it moving vertically, and this is its distance from the midplane of the Milky Way. And what you see is that there is this very beautiful spiral shape in this diagram. And this indicates, in fact, that there is something special going on. This is only for all the stars very close to the Sun, but thanks to Gaia we can actually map this over the whole disk of the Milky Way. And if you do that, you get this very psychedelic picture. It's full of spirals everywhere in the Milky Way. And if you look closely, they even change character as you go from the inside of the Milky Way towards the outside. And what this is very clear evidence that the disk of the Milky Way is not in equilibrium. It's been disturbed recently by some event, and we think the timing was maybe of the order of a billion years ago or so, and the disk is sort of still relaxing into a state where this spiral will eventually disappear. And what we think happened, and we come back now to this dwarf galaxy that I mentioned in the beginning, the Sagittarius dwarf galaxy. This one was caught in orbit around our Milky Way about some 5-6 billion years ago, and it orbits the Milky Way, and it will pass through the disk of the Milky Way every now and then, and every time it passes through the disk it creates this disturbance which leads to these spiral features that you see in this particular diagram of velocity versus position. And if you look, what we can also do is we can characterize the ages of stars around the Sun. And if you just make a histogram of the ages, which is more or less what you see here, then you notice that there are peaks about 1 billion years ago, 2 billion years ago, and about 5 billion years ago. And we think these peaks have to do with the moments that this galaxy crashed through the disk of the Milky Way, and then extra stars were formed by the agitation of the gas, etc. And one of the things that was noticed when we put this out as a press release by a journalist said, hey, this is more or less the time the Sun was born, about 5 billion years ago. Now again, this is very nice. We don't want to make too much out of it. It's probably a coincidence, but interesting nevertheless. Okay, so thanks to the measurement of the motions and positions of stars, we have very good evidence that the Milky Way disk is still relaxing from an important disturbance. The latest about 1 billion years ago, and that's one way we can look back in time. Here's another example. Again, we look at motions of stars, and we know that there is a collection of stars in the outskirts of the Milky Way, so well away from where we are at the position of the Sun. And these stars have very specific motions. First of all, they tend to be on very elongated orbits, so they go around in very elongated ellipses instead of in circles. And they also tend to go around the Milky Way in the opposite direction to the majority of the stars. And that's a clear hint that they were added to the Milky Way at some point after the Milky Way was already formed. And this is what you see in the next simulation. This was done by the group of Amine Helmi in Groningen. And you see the little galaxy down here. Actually, it's not that small. At the time, it was about a quarter of the mass of the Milky Way. It crashed into the Milky Way, and if you look very closely at the red stars, you can see that they're going around clockwise, whereas the others are going around anti-clockwise. And the fact that they're moving in opposite directions around the center of the Milky Way allows us to recognize these intruders from the motions of those stars. And again, we know the ages of the stars thanks to the spectral information that we have. We know their compositions, so we can actually prove that this galaxy that was added to the Milky Way about 10 billion years ago came from a different formation event and helped us build up our own Milky Way. So this is something that happened about 10 billion years ago. which is already a very long time ago. It's not too far from the Big Bang, which was about 14 billion years ago. But we can go back even further, and that's the last bit of this story. So this is just to finish up on this event about 10 billion years ago. We recognize it from these stars that have different motions from the rest of the Milky Way. And this galaxy that crashed into the Milky Way was named Enceladus. And that is after the Greek mythical god that is, I think, buried somewhere underneath a volcano and was discovered thus by the Gaia satellite. Okay, so now we want to go back even further in time. We're already 10 billion years ago, and can we look back even further? The answer, of course, is yes. We go back to the map of our own Milky Way, as seen on the night sky. So this is now a black and white rendition, where before we saw the color map. And I mentioned that we had this particular high-resolution spectrograph on board with which we can measure the compositions of the stars. So we can actually turn this map into a map on the night sky of compositions of stars, where all the red stars have a lot of elements that are heavier than hydrogen and helium, and these are stars that are typically relatively young, and the bluish ones are the ones with very little of these heavy metals, or of these metals in their atmospheres. And those are the types of stars we're looking for, the ones that are probably the oldest. Now this is only for about 5 million out of the 2 billion stars that we measured with Gaia, so it's a relatively small sample. But remember, we also had the other spectroscopic instrument on board, which produces these low-resolution spectra. And this you can do for everything that we have in the Gaia catalog, so for all 2 billion stars. Now with the latest data release, we put out those spectra for about 220 million stars, and a group applied machine learning techniques to take out of those low-resolution spectra the very faint hints of which stars are rich in metals and which stars are poor in metals. And looking for the ones that are really poor in metals, they found a population concentrated around the central regions of our own galaxy, the Milky Way. And it's in particular these very blue groups over here. Those are the poorest in terms of their metal content. And we think these are the oldest fragments of the Milky Way as they came together about 12 billion years ago. So this is really more or less the start of the formation history of our own galaxy, hidden all the way in the central regions. Impossible to see on the night sky, but if you have the capabilities of Gaia, you can figure out the ages and compositions of stars, and we use here also their motions and positions, then you can find these things hidden in the archaeological record of our own galaxy. Okay, I think that is it for this talk. Of course, I've skipped over some details. You can now ask, but where did the first stars then come from? You showed us where the first fragments of the Milky Way came from. But that I happily leave to the next speaker.
Questions for Anthony?
I have a question, but when you say that the crash into each other, do you mean they actually crash into each other, or is it more like a gravitational effect?
Yeah, so the question is, what do I mean when I say they crash into each other, the galaxies? Well, they crash into each other as entities, but it's not like the stars are literally crashing into each other. If the Milky Way were to crash into our galaxy right now, as in fact is happening with the Sagittarius dwarf, you wouldn't notice. So it's really what you see in the simulation is the combined gravitational effect of the two very massive galaxies on the motions of the stars. With actual stars colliding, that doesn't happen. That's correct.
Yeah, so in the first part you showed this vertical wobble of the star, but you only have 10 years of observations, right? So how long is the period of the wobble? Is that extrapolated somehow?
Yeah, so what we actually plotted is not the full. Oh, let's go the other direction. All right, never mind.
I remember.
We don't. So what I showed, the star is going up and down, and we only show a snapshot. At one particular moment, the star is either going up or it's going down, or it's just on the way back, so it's hardly moving. And you know the position above the plane or below the plane of the Milky Way. And it's that snapshot that you see over here. This is for a whole collection of maybe a million stars. And we expect normally that this is just a featureless blob. and we didn't expect to see this spiral. And this is one of the things that is so great about Gaia, is because we have these high precision measurements for so many stars. You can pick up these very subtle features in the data.
So how long is the period of one bubble?
I would guess a few tens of millions of years.
Okay. So you measure very small fraction of that.
Yes. Yeah.
Yeah.
I have a related question. What is the origin of this vertical movement?
Well, the origin of the vertical movement, even if there's no disturbance, is that stars are not on perfectly circular orbits without any vertical motion. They always have a little bit of noise in their motion. And because most of the mass is concentrated towards the midplane of the disk, whenever a star moves up, it gets pulled back down, and that way it keeps oscillating up and down. But when it's disturbed, you get this particular pattern in the collection of stars.
Yeah, you showed at the beginning the galaxy formation process, and I was wondering at which point in the galaxy formation we start having stars. So from the get-go, you are having stars, so it's gas that is coalescing, and then...
Yeah, first gas is coming together, so that was also in the picture. So the zoom in down here was only the stars, and that took a little while. But in the next talk, we're going to learn all about when do the stars actually form once you put gas together.
Why do you think that the oldest stars were so concentrated around the center and that all have been hanging out in like a halo farther away, right?
Yeah, so there is of course also an old population in the halo, but then that tends to be a bit younger than these fragments in the very center. So we think these are the very first protogalactic fragments that formed, if you remember the simulation, and then came together to form the first core, say, of the Milky Way, and the rest is actually sort of built up around that.
They weren't expelled or anything?
No, they sat there. I mean, once the Gaia Enceladus galaxy crashed into it, some of them might have been expelled. That's possible. Probably not, because they're very deep down in the potential well of the Milky Way.
Due to gravity.
But yeah.
Final question?
I understand that Gaia measured about for 1 billion stars the decades, which is 1% or 0.5% of all the stars in the galaxy.
Yep.
So I guess that the field of view of Gaia is only a small part of the whole Milky Way.
No, so Gaia has, so the question is, we've measured only about 1%, even though it's 2 billion stars. Gaia is an all-sky mission, so it looks all around, but it can only go to stars of a certain brightness. So depending on the types of stars, we may see about a quarter or a half of the disk of the Milky Way. But if you're looking at very intrinsically bright stars, we can see all the way out to the Andromeda galaxy, for example. So depending on the type of star you're looking at, you can cover the whole Milky Way volume. But most stars that we see with Gaia are relatively near the Sun.
Can you look through the disk to see stars on the other side of the Milky Way?
To some extent, but right in the midplane, no, because dust there blocks our sight, because Gaia is in the optical, so we cannot see through the dust. Yeah.
Okay. People with remaining questions will have to catch Anthony during the break. So let's thank him one more time.